In this video, we'll do our first test of significance. So here is the situation, trying to be as realistic as possible, but a participant in a raffle observes a very large jar containing yellow and green jelly beans. The participant theorizes that 36% of the jelly beans in the jar are yellow. Now this jar is so large, it would be impossible to count all of the jelly beans. So they decide to draw 1,600 jelly beans, and this is done with replacement from the jar. And we're going to assume here that every jelly bean in the jar has an equal chance of being selected. Of the 1,600 draws, 540 yellow jelly beans were counted. Could the participant be correct? So for a test of significance, your textbook breaks it down into steps. Step 1 is to set up the null hypothesis. What we're going to do is try to disprove this participant. So the null hypothesis is what they believe to be true. So the null hypothesis is that 36% of the jelly beans in the jar are in fact yellow. We also want to set up a box model for our situation. So we'll have one represent a yellow jelly bean and 0 to represent a green jelly bean. We don't know how many are in the box or in the jar, but we do know the percentages. We know 36% of the tickets, of the jelly beans rather, are yellow, which means that 64% of the tickets in our box model must be 0. The number of draws is the size of our sample, which in this case is 1,600. So that is the null hypothesis. The alternative hypothesis is essentially the opposite. And that is the percentage of yellow jelly beans in the jar is not 36%, and that's what we want to try to prove. Step 2 is to pick a test statistic. This is not an easy step. Luckily for the final, you'll only have 2 options. You'll either be able to pick the Z statistic or the T statistic. Next week, I'll also introduce the chi-squared statistic. So, if we have these 2 options, which do we pick? The T statistic is for when we have less than 25 draws in our sample. This is not our case. We are taking 1,600 draws. Our sample size is 1,600, which is greater than 25. So we'll do the Z statistic. The formula for the Z statistic is Z equals the observed value minus the expected value divided by the standard error. So the expected value comes from our null hypothesis. We're going to keep everything in percentages. Our null hypothesis says that 36% of the jelly beans in the jar are yellow. So our expected percentage of jelly beans that are yellow is 36%. The observed value is what we actually got, what was actually in our sample. So I go back up to the problem, and it said of the 1,600 draws, 540 were yellow. So we take the 540, divide by 1,600, and multiply by 100%. And you can check this, but we should get that the observed value is 33.75%. If you find that is not correct, please let me know. We also want to calculate the SE, the standard error. Since our expected and observed value is in percents, we're going to use the formula for the SE for percent, which is the SD of the box divided by the square root of the sample size, the number of draws, times 100%. So the SD of the box, we'll use the shortcut, that's 1 minus 0, times the square root of the percentage of ones in decimal format, that's 0.36, times the percentage of zeros in decimal format, 0.64, divided by the square root of 1,600 times 100%. And again, check this answer, but I got 1.2%. Now we plug that into our Z. So we have the observed value is 33.75 minus the expected, which is 36, divided by the standard error for percent, which is 1.2. And I got negative 1.875. Again, check these answers. They could be incorrect. Our last step is to compute the observed significance level. Which is almost always denoted by P. What we're looking for is the area under the normal curve to the left of Z. Now it's to the left of Z because Z is negative in this case. If Z were positive, we look for the area under the normal curve to the right of Z. So looking for the area under the normal curve to the left of negative 1.875, go to the normal curve table, looking for 1.875. Well, it's exactly between 1.85 right here and 1.9. So we'll go with the smaller value, 93.57. That gives us the area between negative 1.875 and 1.875. Because we want the area to the left, we do 100 minus that area between, divided by 2. And that will give us 3.215%. The important part is P is less than 5%. That is statistically significant. Well, that isn't strong evidence against the participant being correct. It is evidence against the participant being correct. So we would conclude that the participant probably was not correct. That the percentage of yellows in a jar is probably not 36%. If you have any questions, please ask in the questions and answers discussion board.